I'm going to discuss an example of adding angular momenta, and for those of you who are interested, this is actually taken from the 2009 paper, question 9. I will give details as I go along. So the first part of this question asks you to show that for a system where you're adding together L and S, we've got for J is equal to L plus S, that, let's say, J squared can be written as L squared plus S squared plus 2 LZ SZ plus L plus S minus plus L minus S plus. This is a fairly simple thing to show. We start by writing that Jx is equal to Lx plus Sx, etc. And then note that J squared is equal to Lx plus Sx squared plus Ly plus Sy squared plus Lz plus Sz squared. Now you can multiply those out, and what you find is that you end up with L squared plus S squared. Those terms come from the squared parts of the individual bits. And then you also end up with plus 2 Lz Sz, and you get that because you have to remember that Lz and Sz do not commute, and you end up with 2 Lx Sx. Sorry, I said don't commute, I meant do commute. So L and S commute with each other because they act in different spaces. Plus Ly Sy. Now it's actually very easy to show, and I'm going to leave this as an exercise, that this is equal to L plus S minus plus L minus S plus. You show that just by expanding out L plus and S minus in terms of Lx and Ly. And so that's the first part of the problem shown. Now the second part of the problem gives you a state L comma L multiplied, remember this is a tensor product, by S comma S. So that means that ML is equal to L and MS is equal to S. So we have these two states which are a tensor product, and it asks you to show that these are an eigenstate of J squared. And it also asks you to find out what the eigenvalue is. So what we're going to do is we're going to use that formula we just created, and so we show that we have J squared acting on L comma L multiplied by, or tensor product with, S comma S. And that's going to be L squared on LL S S plus S squared on S S LL. I really shouldn't change the order there, but it makes it slightly simpler to see. Normally you should leave the L first, plus 2 LZ SZ acting on this state, LL SS plus we're going to have L plus S minus plus S plus L minus acting on L, L, S, S. And notice that here I've changed the order of S and L. That's because they do commute. Now, L squared acting on L comma L is going to give us an H bar squared L into L plus 1. And then we're going to have the state. So I'm going to put this all in a square bracket because I don't want to keep writing that out. This part here, S squared, is going to give us an H bar squared S into S plus 1. That's because that's an eigenstate of S. Now when we look at the LZ SZ, we're going to get a 2, that just comes from the 2 prefactor. LZ is going to give us an H bar L. SZ is going to give us an H bar S. And then when you work it out, you find that these two terms, the L plus S minus and S plus L minus, both give us 0, because L minus acting on LL gives 0, and S minus acting on SS gives 0. Sorry, L plus acting on LL gives 0, and S plus acting on SS gives 0, because you can't raise those states. So we now end up with the desired result. So we see that J squared acting on this state gives us the state back with a prefactor, and actually you can show rather simply that this is H bar squared into J plus 1, where J here is equal to L plus S. That's entirely what you would expect, and that's reasonable. Now the final part says if we assume that L is equal to 1, and S is equal to a half, there is a state, a half comma a half, which is an eigenstate of J squared and JZ, with values J equals a half and MJ equals a half. Now the question basically asks you to show that this can be written as a sum over the products of the L and S eigenstates. So basically what we need to do is we need to show that a half comma a half is equal to, or can be written as, a sum over states L comma ML S comma MS with a coefficient C ML MS, and it asks you to find the value of those coefficients. Well, the only way that we can get this is if we set ML equals 1, then we must have MS is equal to minus a half, because that then gives you MJ as a half. Or we can have ML is equal to 0 and MS is equal to a half, because that also gives us MJ is equal to a half. If ML was minus 1, which of course it can take on because L is 1, there's no way we can add an MS to that to get MJ as a half. So we only have these two states. So at this stage, we write that a half is equal to A times 1, 1, a half minus a half, plus B times 1, 0, a half, a half. The question then goes on to show, using the fact that J plus on a half is equal to 0. You need to use that to find out what A and B are. So let's do that. We'll use the fact that J plus is equal to L plus plus S plus. And then we say that, so we have J plus on a half is going to equal L plus plus S plus acting on A 1, 0 a half minus a half, sorry, a half plus a half, wrong thing there, that should be a B, not an A, plus A11 a half minus a half. Now, I'm starting to run out of space, but we can finish this off quite quickly. You find that when you do that, if you act with L plus on this 1, 0 state, then you get a 1, 1. But if you act with S plus on the half a half state, you get 0. Similarly, acting with L plus on this 1, 1 state here gives us 0, whereas acting with S plus on the half minus a half gives us a half a half. So we find that 0 is equal to B1, 1 into a half plus A1, 1 a half. All the other terms cancel. So this tells us that A is equal to minus B, and therefore A is 1 over root 2 to get the normalization right, and B is minus 1 over root 2. So this is an example of the type of question that you can actually tackle by adding angular momenta. We started with a simple derivation of a particular form. We then looked at the fact that for one particular case, namely the maximum values of L and S, we can actually have just a single combination of the eigenstates of L and S to be an eigenstate of J. We then looked at another eigenstate, so the L equals 1, S is a half situation where J is a half and MJ is a half. And we derived the coefficients for combining those two by using the J plus operator, that's over here, and using the fact that when that acts on a half, you get 0.